Good morning. It's not afternoon, it's morning because I'm making this video before class today. This is Tuesday, March 17th. So I'm ready to get into material that we need so that you can get the homework done and also proceed down the path of the project. And if things go well, I'm going to push all the way through to the end of chapter 3 during this session. I don't really have any new news on the web page other than I hope everybody is going to be showing up on Slack later today. I put a message out to you guys earlier just letting you know what my plans are. We'll be able to do an interactive video or a screen sharing video. I did this yesterday and it worked quite well, so I'm thinking about maybe changing my video setup and not pre-recording but just recording while I'm doing a session in Slack with the daily app for Slack, which brings up all the video conferencing, and you'll see how that unfolds this afternoon. I guess before I push on to that, I'll just tell you that, show you what it looked like from yesterday. This is the channel for Real-Time DSP, and when I started the session, and get my eyeballs on the right section here. When I started the session, all I did was type /daily. It brought this up, an instant meeting link, and then this was the link that everyone was able to use to get connected together in the video conference. So we'll have something similar when I do the same thing over here under the other channel. So I'm going to jump back into the lecture notes, and then we'll be jumping around looking at a number of different tools, Jupyter, some apps that I've created in Zojo, and some side calculations. But I want to jump back to demodulation of single sideband. We didn't really finish up on that because I jumped ahead to look at mixing, which was needed for lab. And lab is probably pretty much done with that. And of course, lab is definitely done because you can't go over to the building anymore. But that's another story that we can talk about this afternoon in the live session. So we've already seen that single sideband can be coherently demodulated by just multiplying by the coherent carrier and then low-pass filtering. And if you don't have a perfectly coherent carrier, in other words, if this theta of t might be a linear phase, which is, say, 2 pi delta f times t, then we'll get a frequency error, and at the very least we'll get some crosstalk as well because of the way the single sideband operations multiply out, and we'll also have some frequency shifting. So that's all rolled up into the math that you see right here, things that we were looking at the other day. What I want to move on to now is envelope detection using a technique known as carrier reinsertion. This is a fairly old technique. It's been in radio for decades and decades. Amateur radio people use this when they receive single sideband. And I just want to walk you through it because it shows you how you can use an envelope detector, the diode envelope detector or something similar in software, and also the technique of analyzing the envelope of a signal that has another inserted signal. We'll be using that a little bit later in this lecture when we're looking at interference in AM radio systems. So carrier reinsertion just says that rather than doing a multiplication, we're summing in a carrier. And this carrier is shown here as being coherent with the received signal, but it doesn't have to be coherent, and we'll get into that as we move down this pathway. And then this is followed by an envelope detector. So this block diagram has similar elements. It has a circle and a rectangle, but they're not the same thing. Notice here we have a multiplier and a low-pass filter, whereas here we have a summer and an envelope detector. So the waveform E of t coming out of the summer is the ordinary received signal, in this case a single sideband signal, and then the inserted carrier is right here, and I'm going to break that apart or expand it into, factor it out into terms times a cosine omega ct and times a sine omega ct. In order to see what the envelope detector is going to be able to recover, we have to do some analysis to actually find the envelope of E of t. And then that's going to be our final output. So the more general problem of finding an envelope of a signal revolves around this generic expansion, where we have our received signal of the form A of t times cosine omega ct minus B of t times sine omega ct. And if we use Euler's identity and go backwards to write these as complex sinusoids, we see that x of t is the same as the real part of A of t times e to the j omega ct, and then j b of t times e to the j omega ct. And then factoring, we get the complex envelope right in here, and taking that times the complex sinusoid carrier that's present, taking the real part, we get back to where we started from. So this is a real important step, though, in that we were able to identify the complex envelope. And going to a phasor diagram, we can see that the complex envelope R of t has got a magnitude and it's got a phase. So its magnitude is R of t and its phase is theta of t. And it projects down to the real axis as A of t and to the imaginary axis as B of t. It just so happens in this notation that this is the envelope we're looking for. In other words, it's the magnitude of the complex envelope. And that is what the envelope detector recovers. Doing some more expanding here, I've just simply written out that the received signal can now be written in this form if we want to, where now we've got the received signal in terms of its envelope R of t, which is the magnitude of the complex envelope, and the phase theta of t. Right now our primary interests are over here for linear modulation. But later on, when we're getting into angle modulation with the next chapter, then this piece that comes out will be of interest. So we're going to come back to this and we'll see this sort of analysis again. So for now, though, we're focusing just on the signal's envelope. And that will be the output of the envelope detector. Now we have to analyze to see, is that something that's useful to us? Because A of t and B of t are abstractions right now, and we have to line A of t and B of t up with what we have over here. So this is our A of t, and this is our B of t in this case. So I put that together inside the square root, and I have the A of t for the single sideband case squared and the B of t squared, and the square root of that. And we look at that and say, what does that mean? Well, this is what we're looking for is right in here, obviously. We'd like to get our hands on that, but we have the Hilbert transform of M sitting in there, M hat, over here. And we know that's a crosstalk term effectively, so we want to be able to figure out how to deal with that. Well, what we're going to do here, though, is on the carrier reinsertion, which is, this is the amplitude of the inserted carrier. We're going to make that much larger than m of t and m hat of t. As a matter of fact, we're going to choose k such that this condition is true, and then we're going to be able to approximate this square root in this form right here. So that's 1/2 AC m of t plus k. Now the magic behind that is in something known as the binomial expansion, something that you probably saw in calculus somewhere or another. But the binomial expansion applies to any mathematics where you're trying to do an approximation to the square root of 1 plus x. So here it is written out from a math handbook. So the first two terms in the binomial expansion are 1 plus 1/2 x, provided x is much less than 1. So that's the condition that we fall into up here. So we rearrange things to make that happen, and that's what's going on in this expansion. I guess I should probably try to explain how I make that happen. Well, let me just do some erasing on here so I can clean things up a bit. What I'm going to do is we're going to pull out the 1/2 AC m of t plus k, and then what's going to be left in the radical is 1 plus AC m hat of t squared divided by the other term, still squared, 1/2 AC m of t plus k. And because we're making k very, very large, this term is going to be very small. And in our approximation, it's going to be so small from the binomial expansion that essentially in the binomial expansion, we're just going to say, furthermore, this is approximately 1. We're not even going to worry about the 1/2 x, which is going to be an interference kind of term, but we'll be able to focus then on just this piece coming out, which is what we're looking for. It's a constant plus our message. And I'm going to demonstrate that in the Jupyter Notebook here in a second. So now I'm going to demonstrate what happens when the reinserted carrier is not coherent. In other words, there's a small delta of omega inside of there. And if we go through the expansion that we were looking at earlier for E of t, the envelope, after we sum in this large carrier, we can drop down in the math. We can do the expansion like we did before, where I'm going to carry everything through, and I'm going to say the newly inserted carrier is this piece right here, and that dominates because it's going to be a very large, strong signal compared to the weaker received signal. So we'll expand everything with respect to omega c plus delta of omega. And when you do that expansion and finally get it into the form where we can identify the complex envelope just like we did before, we know that it's going to be the square root, or the magnitude of that complex envelope is what we're looking for. And going through the approximation like we did before with the binomial expansion, that means that the recovered envelope from the envelope detector will be, in this case, it's a tone message. And the tone message is the original tone plus or minus delta of omega, depending upon whether or not it's upper sideband or lower sideband. So the frequency error causes the message to shift up and down in frequency, but recovered speech is still good as long as we adjust the reinserted carrier to be close. It doesn't have to be dead on. So let's just go over to the Jupyter Notebook and look at where I set up the demo. So the demo that I have is all done using digital signal processing. But what I'm doing is I'm taking the received signal and I'm inserting a carrier, which could have a frequency error. And then I'm going to form an analytic signal. So this is a slightly different approach than what I was just looking at, but I'm going to form an analytic signal. And I'm going to do that by taking the signal x of t and delaying it. And then I'm going to take a copy of the signal and pass it through a Hilbert transforming filter. And this will form the analytic signal that we've seen before, x plus j hat of t, from our received real signal single sideband. And then I just send that directly into an envelope detector. So in the code cell here, I'm just adding on the carrier. I'm going to start with it at 24 kilohertz like I've done in the past. And then I've done the reinsertion. So in this case, I've done the reinsertion. I've added the strong carrier, and you can see this is lower single sideband, but that spike there is the reinserted carrier. I then form the analytic signal using the function that's in the notebook that we looked at last week. So this is E plus, and what this means by setting this to upper, I'm effectively working with the plus sign right in here. That's all that means. So it's forming the analytic signal, which remember is either a positive only spectrum or a negative frequency only spectrum. It's not perfect. So as we can see in here, and that has to do with the design of the Hilbert transforming filter, I could make it closer to perfect if I designed a narrower bandwidth Hilbert transforming filter. That's kind of another subject. I can pop over and show you something. Well, never mind, it's on my other computer. I can't show you that. But at any rate, this is the suppressed negative image that's down relative to the signal of interest. And this is lower single sideband with the reinserted carrier. I then take the absolute value of that complex signal, and that's going to give me the envelope because it's complex. And there it is. It looks like amplitude modulation. Well, it looks like a recovered message, I mean. So, and then I can go down here one step further and listen to it.
Sockets in the wall, dull green. The child crawled into the den.
So that looks pretty nice, or it sounds pretty nice. Hopefully my microphone picked it up well enough for you to hear. Now if I change this to say 24,200 hertz for the reinserted carrier. Here's the single sideband with the carrier reinsertion, now at a different frequency, so we see some envelope fluctuations already because of the difference frequency. We see the reinserted carrier is still approximately just at the top side of the lower single sideband signal. Go ahead and form the analytic signal. It looks basically the same. We can't see that small frequency error. Form the absolute value of the complex signal. Can't really see that it looks that much different, but when we go to listen to it using the envelope detector, we'll hear the difference.
Sockets in the wall, dull green. The child crawled into the dense grass.
Just like when we were playing with this earlier, with the other demodulation scheme, the pitch has been shifted up in this case, but it's still quite intelligible. We could vary that frequency to make it to our liking, and that's what amateur radio has done for decades and decades. And single sideband, where it's used in ship-to-ship communications and other applications where single sideband still exists for speech transmission, this still works. I'm going to set that aside now, and I'm going to go back to the lecture notes, and we're going to skip over vestigial sideband, which was part of the old analog TV standard. We now still have vestigial sideband in HDTV, but it's in a digital format. But I'm just going to skip over it because we're not going to do anything with it in class beyond this passing over it. We started talking last week about frequency translation and mixing, and this would have been 1 week ago today. The idea of frequency translation and mixing is that we want to change the location of a signal from one frequency to another. So it might come in off the cable and cable TV at F1, and then the set-top box moves it to a new frequency, or any other receiver application that cares about this. It can be a receiver, it can also be a transmitter. So another way of thinking of this operation of frequency translation is F1 is an uplink frequency going to a satellite, and then the transponder on the satellite is going to send it back down to the Earth at a different frequency, F2, and that's a standard transponder operation. That's all that most satellites do. They just simply take the uplink frequency and they send it back down to the Earth at a different frequency, and there might be spot beams involved, or it might just be the whole continental US covered by that antenna system. But that's how TV signals get routed around the country via satellite. They go up on one frequency, they come down on another, and the cable TV companies receive those, and then they redistribute that through their cable network. So the basis of what goes on in frequency translation is we have to pick a local oscillator frequency, FLO, which is what this would be called. And that frequency FLO is going to carry out the moving of F1 to F2. And fundamentally it relies upon the trig identity that we're all familiar with, that would say if you had cosine, I'll just skip the pi in here, I'll just make it like this, cosine of F1 times FLO, that's going to give us cosine of what? F1 plus FLO plus 1/2 cosine of F1 minus FLO. And the fact that the minus term may be negative doesn't really matter because cosine is an even function. So if it helps you understand it better, you can just say it's an absolute value in there. The bottom line is that we're getting the output from the multiplier at two frequencies, a sum frequency and a difference frequency. And we have our choice of which frequency we want to choose in our design, and to make sure we don't have two frequencies coming back out and going further in the system, we have to put a bandpass filter in to eliminate one of the two frequencies. So if we wanted to go to F2, we would make sure that we have a bandpass filter centered on F2, and that would then reject the other frequency. This is a more formal statement of it, just in the mathematics, saying that the two frequencies we get out are going to be omega 2 and 2 omega 1 plus or minus omega 2. I prefer to, I want you to see the math, and you can see it here. I prefer to just draw some pictures to help you understand this, because this is a very simple concept, and it's a back of the envelope kind of calculation that you would go through. So what I'd like to do is just sketch out some ideas here so you can see. So suppose that's a received signal, and we want to move it to a new frequency, and this is the typical radio application. So rather than calling it F1 and F2, I'm calling it FC and FIF. So we'd like to get this signal moved over to there. So how are we going to do that? In order to make that work, we just need to put FLO either above FC or below FC. The main thing that we're looking for is the IF frequency is the difference between our input frequency FC and FLO. So we can either set it above or below. So this would be high side or low side. Just as long as we get the difference there, that's all that matters. The difference would be at FIF, and this is assuming, of course, that FIF is below FC. Sound good? I can't get feedback from you right now, but let's just take another scenario. Suppose FC is down at a low frequency, and we're going to, let's see, be color consistent here. We'll go to green again. So in this case, this would be more like a transmitter case. I'm still going to call it FIF, but it's going to move the signal up in frequency from FC up to FIF. If you want to change the labels to make more sense, we could do that too. I'm just going to keep the same variable names though. So now we need to go up in frequency. So if we look at the idea of forming the sum and difference when we multiply by the local oscillator, what should that local oscillator frequency be? Well, we have, obviously just from the picture here, we have one option. We can put local oscillator down here so that FC plus FLO1 is FIF. So that's one option. So you just simply want to take the sum frequency that comes out of the multiplier. Another option, though, that we can use is we can put FLO2, I'll call it, above the IF frequency. And then I'm going to be using the difference frequency. So then I want FLO2 minus FIF, or not FIF, minus FC to equal FIF. So now I'm using the difference frequency. So I'm setting the local oscillator above the new frequency I want to move to, and I'm going to use the difference frequency to get there. And this is the situation where the new frequency is above the input frequency, whereas this example, the new frequency is below the input frequency. So it's just a different orientation. I like the idea of drawing pictures because the math sometimes is, even though it's so simple, it's a lot easier to just think, where do I need to set the local oscillator so that I can either get a sum at the new location of interest, or I can use the difference to get the new location of interest. So what I'm going to do now is just go repeat this again for a simple example. I'm going to work in megahertz just for convenience. So trying to keep the same colors, I want to move to 10 megahertz, and I'm going to suppose I'm starting, oops, my finger never works properly on this touchscreen. So suppose I'm starting at 50 megahertz. This is FC, and this is FIF. So what frequency do I need to bring my local oscillator in at? That wasn't the color I wanted either. Where do I need to set FLO? Well, I could set it to high side tuning, so I would set it right here, and that would be 50 plus 10, which is 60 megahertz. That works. I could also set it below by 10 megahertz. So that would be 50 minus 10, which is 40 megahertz. So those two would work perfectly A-OK. Hopefully you can see this is not an exotic calculation, and I'm emphasizing the drawing of pictures because I see so many times where you work a quiz problem or an exam problem and you just think of plugging into a formula without thinking what it's really doing for you. If you were to go draw the picture, though, after you got the answer, you'd see, oh, that doesn't really work. What did I do wrong? Well, I think it's better to just draw the picture and understand that I'm either going to solve for the sum or the difference. So let's just repeat this again for an upconversion operation. So in this case, I'm going to assume I'm just going to use numbers this time. I'm going to assume we want to get up to 100 megahertz. So that would be somewhere in the FM broadcast band. And we're going to be starting at 5 megahertz. So we're going to move 5 megahertz signal up to 100 megahertz. So the first thing that comes to mind to me is the sum frequency, because summing just seems more natural. So if I'm at 5 megahertz and I want to get up to 100 megahertz, what do I need to do? I just need to add 95. Add 95 megahertz onto 5 megahertz. So that'll be 5 plus, well, let me back this up. The local oscillator frequency is going to be 100 minus 5, which equals 95. And that way, if I take and form the sum of 95 and 5, I get 100. So the second option is going to be to put the local oscillator frequency above my new frequency by 5 megahertz. So just intuitively from the picture, I'm going to be sitting at 105. So it's going to be 105 minus, not 105, I'm thinking ahead. It's going to be 100 plus 5, which equals 105 for the local oscillator. So the difference frequency again is 5 megahertz. So I could look at the differences in here being the start frequency if I wanted to. I really don't want to say that because I don't want you to get confused. I want you to just think, if I'm coming in on one frequency in red, how do I move to the new frequency in green? So you get two options. You get two options here. While we're sitting here, though, let me just point out another aspect of frequency translation, sort of the dark side of it. It's called the image frequency. So whenever you have a mixing operation, you've always got yourself vulnerable to an image frequency. So what is the idea of the image frequency? We'll just use the numbers right here as an example. And I'm going to try to draw this in a dashed red, or I guess I'll use black. So it is truly dark. So if I set if there's another signal out there that is 10 megahertz above FC, or 10 megahertz above the FLO, I mean. So this was at 60 in this example. And this was at 40. So the image frequency with respect to the local oscillator frequency is, in this case, going to be 60 plus 10, which is 70 megahertz. And what we're seeing here is that there's a spread of 2 FIF between the desired signal at 50 that will move down to 10, and then the image signal at 70, which when converted with local oscillator of 60 also moves down to 10. Does anybody see a problem with that? The problem is that you're wide open to this image signal. Likewise, if I was to use the local oscillator at 40 megahertz, I could have an image frequency for that be down here at 30. And that will be, again, 10 megahertz away from that local oscillator, and that will convert down to 10 megahertz as well. So there's always the chance of having an image frequency get into your receiver, and the main issue, from going back to the picture over here, is that an image frequency will now pass through the bandpass filter and it will show up right on top of your desired signal. And that image is talked about here in the notes as being right here. Just flip back over. So it's going to be omega LO will be the input, omega 1 plus or minus omega 2 will be a valid image frequency. You'll have to think about that, but again, the math here is sometimes confusing because we always have two options, plus and minus. So again, I prefer to think initially in terms of a picture, so you can just kind of settle on what can happen from these pictures in terms of getting an image. Same idea holds in the upconversion operation. Another signal that comes in could get upconverted to 100 as well. Should we take a look at that for a second? If we're mixing with 95 megahertz, what other signal would come in at, would get moved up to 100, for example? So we could home in on this, get this to switch. So where would the signal have to be to get converted to 100 from 95? Just check this out. If I put a signal at 195 megahertz, that minus the 95 local oscillator will sit right at 100, so it will land right on top of our desired signal's new location. Likewise, if I am picking the other local oscillator signal, 105 and 100, that will be 205. So 205 minus 105 lands at 100 as well. So it works in both scenarios of either upconverting or downconverting signals. They're much higher in frequency, but they're still sitting around there. They're at 205 and 195. So I'm going to talk a little bit about how you avoid images or keep images out of your converter with this example right here. The bottom line is we're going to be able to put a bandpass filter to reject the images. And if we're making a tunable receiver, then that RF filter needs to be tunable as well. So this is a block diagram for a simple AM broadcast super heterodyne radio. The term super heterodyne was coined, I think, back at the turn of the last century when Armstrong, one of the pioneers in radio, I'm pretty sure it's attributed to Armstrong, came up with what he calls the super heterodyne principle. And it's the frequency translation idea, where you have a local oscillator and you move the signal of interest to a common intermediate frequency so that it can be doing all the gain and the signal processing at one frequency, and you just make the local oscillator tunable. And that's used in everything radio, whether it's your cell phone, Wi-Fi, car radio, you name it. Everything does mixing like this and moves things to a common frequency for convenience. So in this case, AM broadcast is 540 to 1600 kilohertz. The stations are spaced every 10 kilohertz. And the common IF frequency that people like to use in broadcasting for AM is 455 kilohertz. So we need to move a local oscillator in 10 kilohertz steps in such a fashion that it can convert a signal between 540 and 1600 to 455 kilohertz. So if we go with low side tuning, then we're going to set the local oscillator always at the desired signal minus 455. And that makes the local oscillator then have to tune from 85 to get to the lowest frequency up to 1145. If we decide to go with high side tuning, which is the more popular option for this scenario, we will add 455 to the range of received frequencies and come up with the local oscillator needing to tune from 995 to 2055 kilohertz. The main reason why the high side tuning is so significant here is that the ratio of the min to max or max to min local oscillator frequency is the smallest. So this ratio here is only 2.15, whereas over in this case it's 1145 over 85. And if I open up my Jupiter QT console, that's a tuning ratio of 13.47, which is, if you're designing an oscillator, that's a huge, that's over a decade of ratio of frequency tuning, which is generally something you want to avoid. Now, in most receivers today, the local oscillator is tuned with a frequency synthesizer, and it's done digitally, but it still has to produce an analog local oscillator. So the picture down below kind of shows the setup. I've just got one example in a bullet here, but I'll just go through the picture because I think it explains it well. This is using high side tuning. So I have a signal at 560 kilohertz, and I would like to push that down to 455 kilohertz. So I make my IF frequency at the sum of 560 and 455, so that puts it right here at 1015 kilohertz. One IF frequency above that, which is at 1470, which is also in the AM broadcast band, that is where my image frequency sits. So potentially that image will also get down converted. And that's what I'm showing down here. But if we put the bandpass filter at the front of our converter, frequency translator, if the bandpass filter is as shown here, nominally, it's not going to be a brick wall like that, but have adequate attenuation so that it doesn't let any of the image frequency get in. The sum frequencies are also shown in the last two sketches. The output of the mixer when you're converting 560 has a sum at 1575, and the image frequency when it gets converted, it's up at 2485. Those get rejected by your IF filter though, and the IF filter generally is got a very steep skirt in its frequency response. So there's really two aspects in the super heterodyne principle and the frequency translation idea: rejecting images and the ability to have good selectivity, which is controlled by the IF bandpass filter, and the ability to have rejection of nearby signals that might be hanging out either side of the IF frequency. Why do I say that? It's because there's going to be adjacent signals sitting up inside of here. Fails to work for me once again. So there'll be adjacent signals in the AM broadcast band, and those guys are going to convert and be alongside of the mixer output. But as long as you can reject them with your IF filter, they won't impinge upon any of the receiver electronics. And when I mean impinge, they're obviously not going to be maybe directly demodulated, but they could overload the signal processing chain and cause issues. A second example I put in here is the double conversion receiver, and it is much nicer, and this is the exact block diagram from lab number 4, which those of you taking the lab have been working with. The dual conversion receiver has some nice attributes to it. It takes more hardware, but it has some nice features. So in this case, we convert once to a high intermediate frequency at 10.7, and do that with the local oscillator. The local oscillator, and this is, in this case, the scenario is weather channel number 4, which is here over in Manitou Springs, 162.475 megahertz. We're going to pick high side tuning by setting the local oscillator at 173.175. That creates sum and difference of 10.7 and 335. 10.7 IF filter passes that difference frequency, and now in order to get good selectivity on this particular form of broadcasting, which is we're gonna learn about in the next chapter, narrowband FM, we converted a second time to 455. So we'll use a fixed oscillator here, and on the radio board in lab 4, that was a crystal oscillator running at 11.155. And when I designed the radio, I went to a company and said, make these crystals for me. So it was a special order crystal, and that's not uncommon in certain types of radio applications. So why is dual conversion so nice? Well, dual conversion allows good image rejection because the image is going to be another 10.7 megahertz away from the desired signal. So it's going to be a total of twice the IF frequency away. And that makes it easier to reject the image. When you have a low frequency IF, it's just 2 times the IF, remember. Your image that can leak through is a lot closer in frequency. So it's not unheard of to actually upconvert in the conversion as the first stage of conversion so that your image is a long ways away, and then downconvert it a second time. Because once you convert it the first time, this first bandpass filter is going to be good at removing your images as well. And then you get your selectivity from this to be able to pass only the signal of interest. I would say any questions, but you'll have to bring those up this afternoon. Mixers is the next little topic in here, and I just want to go through some fundamentals of a mixer. A mixer is implementing the multiplier. So multiplier and mixer are synonymous with one another in radio electronics. Mixer is just a more appropriate term, as this second bullet says, because an ideal multiplier is rarely available. The idea of mixing signals is what is of interest, and this goes way back to the beginning of radio. The notion comes from bringing two signals together, summing them together. Suppose we bring in two signals into some nonlinearity. Well, there'll be many terms in a nonlinearity. There'll be a linear term, there'll be a square law term, cube law, and so on. But if we consider just the square law term, that gives us what we're looking for. That's kind of the main deal. So if you operate a device slightly in the nonlinear mode, you do get a second order term, and that contains the mixing products of interest. That contains the x1 times x2. But you get a lot of other terms that come out of it. And those of you in the lab have seen this. A general mixer concept might be this block diagram here, where you've just got a sum of two signals, a local oscillator and an RF receive signal. Could be active and passive devices. When I say passive, I mean diodes, but it could be transistors, FETs, and so on. This is a metal-enhanced semiconductor field effect transistor active mixer, which is just using the two gates of the device to bring the signals together. The lab is using a double balance mixer, which is constructed of a diode ring and some transformers. So this is another popular mixer in passive electronics, using the diode ring with diodes on a substrate that are all matched. They're generally Schottky barrier diodes because they have a very low turn-on voltage and they switch fast. And then you have transformers to go from what would be called an unbalanced single-ended signal form to a balanced form. So you've got the opposite side of the transformer's got a center tap to ground, and that arrangement drives the diodes. There's passive and active double balance mixers. The mini circuits double balance mixer that's used in the lab looks like this. An active mixer available from Maxim looks like this. So just to see how easy it is to get mixing action going, I put together a simulation in Keysight's ADS. ADS is Advanced Design System, which we have in our department. Have available actually through the VPN if you know what machine to log into. It's also in the COM lab. Here I'm just bringing together an amplitude modulated signal at 560 kilohertz, and I'm creating AM using an AM transmitter. Let me back up for a second because I haven't looked at the schematic for a while. I'm using an AM modulator block, which is available in ADS, and I'm feeding in a 10 kilohertz message signal in a 560 kilohertz carrier. And then I'm adding with a signal summer in a frequency at 10.15, and based on my analysis for mixing operations, I'm looking for the difference frequency, but I'm also going to see what the sum frequency is. So when I LO mix, I get a 455 kilohertz output, and this is a spectral plot that comes right from ADS. The input signal is also present, And if I was to move up in frequency, I would also see that there's going to be some LO leakage coming out of this simple setup because I don't have a filter out here. All I'm looking at is sending that sum signal into a diode, a 1N4148 diode, and just letting it form a signal that I can get the power spectrum of. So that works, and it works quite readily. It's just that now you have to clean things up. So the last topic before we move into sampling theory is interference. And this will just be a brief introduction to the idea of interference, but all communication systems are subject to interference. So what we'll do in this model is we're going to assume that the interference lies close to our desired carrier frequency Fc, and the offset is all we're going to care about, is Fi is the interference relative to the carrier. So in my picture, I'm supposing we're going to receive AM modulation, and we have single tone interference, a carrier from an interfering signal, intentional or unintentional. You could call it a jamming signal too, is sitting up there in red. So if we come in to our coherent demodulator, we just have, this is the interference, and if we multiply by our standard coherent carrier, what we're going to get is the desired signal. We're going to get the sum signal, and we're going to get the double frequency term, but I'm assuming the double frequency term is going to be removed, so in the end we'll just get the desired message signal back. This is tone modulation. So I guess I should say this is AM with a tone message. And then the interference comes back too. So the interference is present. But if that is at a high enough frequency, what can we do? We can just simply do what? We can protect ourselves by putting a filter in. Age-old problem. So bandpass filter can be used to protect ourselves from adjacent channel interference. If the interference decides to land in the same band where we're at, we are not going to be able to deal with that very well. If that becomes a very strong signal compared to our weak received signal, then we can be wiped out in the coherent demodulator case, because this could dominate. And if that was a modulated carrier with digital modulation, and we were modulating not with tone modulation but digital modulation, it might cause such a problem that we can't recover our data bits. If we're doing an envelope detector, like we were talking about earlier for AM modulation, we have to consider two different terms, or two different scenarios. We have the case where the received signal of interest is much stronger than the interfering term, and then we can go back to our envelope modeling that we were doing at the beginning of this lecture, where we find the complex envelope. And when we solve out for with the complex envelope, this would be the complex envelope right here. And then we go back to using the binomial expansion. And we see that we'll get back the DC bias from the carrier, the message signal, in this case it's a tone message model, and then we'll get the interference. it's acceptable. We just have to mitigate it in the same way we did for the coherent demodulator. So once we put the DC block in there to remove the pure carrier from our envelope detector, we're fine. But now if we go on to this scenario where the interference is much stronger than the signal of interest, we're going to see something very, I didn't draw a picture of it, but let me just draw the picture down here, what the spectrum looks like. So that's the AM signal of interest, FC. But now this interfering signal is a monster sitting right over here. And now the coherent demodulator can still function as long as we demodulate with FC. But if we do an envelope detector type demodulation, what it looks like, and this is pretty interesting. This is an abstraction, but it looks like this is LSSB tones, and this looks like a reinserted carrier. So the envelope detector is very confused at this point because of the strong interference, and the words are matching this picture. Everything gets referenced to that interfering or jamming signal. So all of the frequencies that come out of the detector are shifted by that strong jamming signal's frequency. And we say effectively the message signal is lost because the overpowering interfering tone is confusing the envelope detector. I just remembered I had some other demos in Jupyter that I wanted to go through, so I'm going to jump over to those because these are useful in the homework problems that you're working on right now, the ones that are due on Friday. So what are those homework problems? Let's just go look at them on the website. You've got to turn in 2 problems, or you're going to be emailing me in PDF 2 problems. So the first problem is just working with the Weaver single sideband modulator, which you implement for project 1, but in this problem you're just going to, I can't draw on this, but you're just going to be putting in tone modulation, and then assuming ideal filters everywhere, which is just 2 filters, 2 low-pass filters, you're going to just work through the math stage by stage. And I recommend when you do this that you just put labels on here. Let's see if I can get away with something here. See if I can paste this over. This may not work, but it seems like it should work. Yep. So this is just back over in my other tool. What I recommend when you do this, you're going to call this, say, X A, XB, let's say, and this will be called YA, YB, ZA, and ZB. So you just go through the math in the time domain and do all these multiplications using the trig identities, and then you'll be able to come down to saying XC. If I choose the sum solution, I'm going to be adding ZA to ZB, and if I choose the difference solution, I'm going to be subtracting ZA from ZB, and this is a cosine omega MT. So you want to be able to show that you're putting up on the carrier. You want to be able to show up here when you go through the math that you're going to be putting out up here cosine omega C plus or minus omega M of T. That's what you want to be able to establish. With the plus sign, you're going to be putting out upper single sideband, and with the minus sign, it's going to be lower single sideband. So by working through this math, you'll gain confidence in what you're building in Project 1 in the code is indeed going to function. The analysis here is just simply for tone modulation in this homework problem. Again, I'd say, are there any questions? But we'll get back into this later when we have the live session. Remember, the intent of the live session is not for me to repeat my entire lecture, but to just home in on specific issues that you might want to bring up. Okay, so we'll come back to this in a second, but I want to show you also what problem 3.2 is all about. This is an analysis of image frequencies, and it's a pretty easy pencil and paper problem, but I do suggest, or in the hints page I at least say, that you might want to try simulation to get a better understanding. So looking in Jupyter, I'm reviewing through frequency translation and mixing right here. And then I have a function that was defined earlier in the notebook that creates M sinusoids. So what I've done is I put up a bunch of sinusoids centered on 10 kilohertz. Let me see. Remember how this function works again. Number of samples. I'm going to do 10,000 samples, and I'm going to set a collection of frequencies. For F, I'm going to set the amplitude value, and I'm going to set the phase, and the sampling rate. So the sampling rate is 200 kilohertz, the phase is 0, the amplitude values are here, and these are the frequencies of the tones. So this is the desired signal. I'm just trying to build up a transmit signal. And then here I'm building up an interference signal, and here I'm going to set the carrier frequency at 30 kilohertz, put in this collection of tones for this being a message signal, and then do the same for the image. I'm going to put the image up at a frequency that's 40 kilohertz, and then I'm going to choose a local oscillator frequency at 35 kilohertz to demodulate it. So I run that cell, then I draw the picture down here, and let me interpret what's going on here. My transmit signal is at the blue one, so that is at 30 kilohertz. My IF frequency is down here at 5 kilohertz. So the blue signal with the local oscillator sitting here at 35 kilohertz is getting mixed down to 5 kilohertz, right? If I'm at 30 and I mix with 35, I get a difference at 5. But then I also have an interfering signal sitting over here at 40, and that's the image frequency relative to my 30 kilohertz signal. So it will mix with my local oscillator at 35, and it lands over here as purple. So that's the image mixed. And then I've also drawn here what are the sum frequencies for the mixing operation. So this green one is the mix, so it's 35 plus 30, so it's sitting there at 65, and then the purple one again is 35 plus 40, so that's 75 kilohertz. So you can play around with this if you want to help kind of understand what's going on with the basic mixing idea. The tone generation or the multiple sinusoids is just to create a spectrum that has width to it. So you can see that it's not just a spectral line, and distinguish between carrier pure sinusoids, which is this LO signal, and then the two modulated signals. This example, I'm not going to go over envelope detection, but now we're going to move into sampling theory. So sampling theory is something you've seen in 2610, and I think you revisit in 3205. The idea is that we're going to take uniformly spaced samples of a continuous time signal and then use those samples within our system to do further processing. Like if it's a pulse code modulation is our primary example that we're headed towards, but it could be other pulse modulation types. But some means of converting an analog signal into samples and then representing each sample with a digital word is the more common scenario. So basic sampling theorem is low-pass signal. So you sample a signal whose spectrum is 0 when f is greater than w. The sampling theorem says right here that we just need to choose fs greater than twice that highest frequency w, and then we can reconstruct from the samples. The 2w is called the Nyquist frequency. Fs, half the sampling rate, is called the folding frequency. And to prove it, I've just used Fourier transform theorems, which we've already seen. We know that the sampling waveform itself, this was talked about earlier, has a spectrum which is this. So when we looked at that in chapter 2, we really didn't have an instant application for it, but it was used in that other theorem. At any rate, we can see that when we sample a signal, we get, in the spectrum of the sampled signal, we get images at multiples of the sampling rate, fs. So after we sample the signal, we get all these frequency translates located at multiples of fs. And the two pictures I have shown here are if you're sampling at greater than twice the highest frequency, then you can separate in the reconstruction operation out the principal translate centered on 0, and you can recover then from the samples the original signal. If you violate sampling theory and don't sample at greater than twice the highest frequency, then the images overlap each other and you have aliasing, and it's not possible to get back what you started with. The bullet here just explains that idea. It explains the idea of the ideal reconstruction filter, and then in the picture here it's the ideal reconstruction filter, which is of course going to be done with a realizable filter. For the case of the ideal low-pass filter, the function that gets the waveform back is the sinc function. So this interpolates samples to the waveform. And you've seen that before, so that was just a quick summary of that. What is new, though, you've never seen the sampling theory for bandpass signals. So just take a brief look at that. I'm getting kind of fatigued myself, so I may not get as far as I wanted to, but I'm going to see, because we're pretty close to pushing on to the end of this chapter. For a bandpass signal, the assumption is that the spectrum is again 0 for f greater than some upper frequency, fu, but fs, for the case of the bandpass signal, can actually be chosen to be lower than twice the highest frequency. So, and that depends upon the bandwidth of the signal. So we have this factor of m, which is related to that upper frequency divided by w, and it's the greatest integer less than or equal to that ratio of the upper frequency over w. So to put that into action, and then I'm going to animate that here momentarily, suppose this is a bandpass signal of interest. Its bandpass spectrum runs from 2 to 4 hertz. The bandwidth of the signal is 2. This is what would be called the RF bandwidth. The upper frequency is 4. The ratio of the upper frequency over W is 2. So M is equal to 2. And if we plug that in, we see that we can do that sampling rate. Otherwise, the low-pass theorem said we'd have to take twice the upper frequency, which would be 2 times 4, which equals 8. So we can get away with a lower sampling rate on a bandpass signal if things line up nicely. This is effectively what's going on when we're sampling at the lower frequency. We're interleaving aliases lower in frequency than the bandpass signal, but we assume we can recover and actually I wrote it down over here. I just didn't pay attention right away. We can use a bandpass filter to recover it. This also has implications in software-defined radio. So let's go take a look at that. I have some functions in here that can do bandpass signal spectral representations. I'm not going to play with those right now. I'll save those for the next lecture. But what I do want to do is show you some apps that I wrote in a GUI programming language known as Zojo, which is a cross-platform development language. This first app is just showing you the basics of sampling theory in the time domain. Just a quick review of things that you learned in prior classes. I'm assuming here that I'm sampling at a fixed rate of 1 hertz, but I'm going to change the frequency of the input sinusoid. So here I can increase the frequency of the sinusoid, and as I get up close to the midpoint here, we'll see that we're going to reach the Nyquist rate. So we're sampling right at twice the frequency of the sinusoid, so we're getting a sample at the peak and a sample at the valley. If I was to phase that sinusoid relative to the sampling clock, which is what I'm doing with this slider, look what can happen. You get nothing. And that's why you have to sample at strictly greater than twice the highest frequency so that you don't have this scenario take place. In general, the sampling clock is asynchronous relative to the signals, so if there was a sinusoid present that was being sampled, this situation would not exist. But this can happen. Moving the frequency of the input up further, we're going to reach a point here because now we're violating the sampling theorem. We're going to reach a point, though, where the sample values in blue, our eyes are going to start to be able to see the alias frequency. And where that happens is different. I'm seeing it right now. If I follow these samples down, I can see that there's a lower frequency. If I keep pushing the slider up, though, it's more obvious now, right? And if I keep going, I can definitely see the alias. So the alias is the sinusoid that I see from the blue dots. And of course, if I keep going further, it just becomes a constant again. Even though the frequency is high, it's at 1 hertz now, we're not able to reconstruct the proper frequency, so we have aliasing. Or if I turn this on, then that button just says as we sample, as we bring the frequency up higher and higher, we reach the folding frequency, which is 2 samples per cycle, and then effectively what comes out of the sampler is the alias frequency. So the red is now the alias frequency going down. Enough of that. This other app is looking at things in the frequency domain. So here I've just got the slider set up so that I can change the ratio of the sampling frequency divided by the bandwidth. And if I'm doing low pass sampling, I need to have that ratio be greater than 2. If it's less than 2, then I have aliasing. But now what I want to show you is when I switch to a bandpass signal, a signal that's bandpass in nature. Here I'm sampling at greater than twice the highest frequency, so the spectral images are in red, the principal images in blue. But now we can see how the bandpass sampling theorem applies. If I reduce the sampling rate, initially I'll get some interference, in this case some aliasing, but if I reduce it further, I hit a clear zone. If I keep going down and down and down, some more images start to come into play. I'm still good to recover the blue signal though. Starts to interfere again, and then I reach another zone where I'm clear. And I can keep dropping down depending upon the ratios of the bandwidth and the center frequency. I can finally come all the way down. Let's see if I hit the right spot. Didn't do that right. That definitely doesn't work, but there's another zone in here. There. At this ratio of 0.4, fs over b to 0.4, that's the lowest I can go, but this is not very practical because I need to actually have some guard band in frequency to pluck out the bandpass signal. But you just can see that you can get by with lower sampling, and in reality, in software-defined radio, the undersampling operation is not to get back the blue signal, but to capture the signal that's right down here centered on 0 frequency. So we get frequency translation or frequency conversion and sampling happening all in one step. So we digitize the signal and then move its spectral samples down to baseband, and we can, depending upon how you do this, what's down at baseband might be like that, or it might be oriented in the opposite direction. I mean, the spectrum might be flipped or not flipped, but that's not really always the most important part about this. But at any rate, that's it. Hope you find that interesting. These apps are available on the website. These apps were part of the Signals and Systems for Dummies book originally. So the next section in here, which is analog pulse modulation. And the reason why we reviewed sampling theory is to be able to go through various types of pulse modulation. So pulse modulation implies there's some sampling rate going on, or some sampling operation. The simplest is pulse amplitude modulation, where we just simply sample the waveform at a regular interval and then represent the waveform in terms of its samples, still spaced on the time axes though. You can recover the signal just with a low pass filter. In this case, the sampling waveform is not ideal. It's just narrow duty cycle pulses. This scheme of PAM, as it's known, pulse amplitude modulation, was used a long time ago in aircraft to distribute audio. And most of you are too young to remember this, but some of you might. John, you probably do remember flying and having a sound tube that you would plug into the armrest and you would listen to programs through the sound tube. And that was a multiplexing scheme that was built on top of pulse amplitude modulation. Another type of pulse modulation is pulse width modulation. This is popular in control systems, popular in robotics where you're controlling the speed of a motor. And now it's become popular in high efficiency audio amplifiers, Class D power amplifiers for audio. So pulse width modulation just represents the amplitude of the waveform by a pulse width. So when the amplitude in this picture is very negative, like it is here, you send a skinny pulse. If it's very positive, you send a really fat pulse. Another pulse modulation type is pulse position modulation, where you have a time slot that you send your signal in depending upon whether it's positive or negative. So here you have a slot, and if you're negative, you send it early in the slot. If you're positive, you send it late in the slot. And that's PPM. Delta modulation is also grouped in with this. Delta modulation is for encoding, and it used to be used for certain types of audio transmissions. Telephony used it. It's always surrounded analog modulation, though, where the message is encoded. So with delta modulation, you send the difference between the pulse, or between the amplitude and the previous amplitude sample. So you have a pulse modulator that limits, and then you feed back the difference. So what you're sending at the transmitter is a series of pulses, plus and minus pulses, and they're following the waveform. And you have to sample, you have to use small enough delta values so that you can get fidelity in the waveform, but you have to also sample fast enough so that you can follow changes in the waveform. And the phenomenon I have highlighted there is slope overload, where the signal might be changing so fast that with the small steps you can't track it. I originally built examples of this in MATLAB, and it very much dates me because this example was written in 2006. These pulse schemes that we just talked about are not that much of a focus for us. They're legacy, though, and you might bump into them in some legacy system. The final scheme, though, is pulse code modulation, and this one is very much a going concern. Pulse code modulation is basically analog to digital conversion and digital to analog conversion. You sample, you quantize, and you encode. So the top blocks just show it abstractly. PCM is what you get as your output. If you want to look at it just in terms of electronics or digital electronics, you have a sample and hold, and you have an A to D, and then you'll have a parallel to serial converter. Frequently, this is all together in one chip. Or in a microcontroller. So you'll have the encoding operation, then you'll have the decoding operation. So this is the encoding operation, and then the decoding is the reverse of that. So the idea of PCM is you take and encode amplitude levels into a binary word, and then you send that binary word as a string of characters, zeros and ones. I think I'd like to do a wrap-up on this either tonight or next on Thursday. This is a scheme that's used in compact disc digital audio, and it's used in a lot of other audio applications. You will be using this when you do project number 2 later on. So I do have that built up. I actually have functions for encoding and decoding in Scikit DSP-Com's digital comm module. So, for example, I can encode an audio string, and I'm going to leave you with this example right now. As a final example, I'm going to take speech. I'm going to take 120,000 samples of speech, and then I'm going to encode it using 8 bits per sample, and that is selectable, and you'll be playing with this in the second project. The number of bits I want a PCM encode, and then you feed in the analog samples, and it encodes it into a bit string, XE, and then I can send it through a radio channel or a simulated channel that adds noise to the samples, and then I can PCM decode it, which takes the bit string, and you tell it how many bits per sample you're going to be decoding it with, and that comes back from here. And then because I'm adding noise in this case, I'm setting the signal to noise ratio at just 10 dB, so there's quite a few chances of making a bit error. In this case, 800,000 bits were sent through, and 5 bit errors occurred. And if we go ahead and listen to this,
the little tales they tell are false. The door was barred, locked, and bolted as well. Ripe pears are fit for a queen's table.
okay, you probably didn't notice it, and I'll have to go through this again. There are a few pops and clicks in there, and those were the 5 errors. Maybe what I should do is just take this down, and you'll see what happens if I drop this down. Take it down to 6 dB. Then I had 18,000 or 1,800 errors. So if I play that back, it'll definitely sound raspy.
The little tales they tell are false. The door was barred.
So that's the impact of bit errors on this system. And if I look at the waveform under that scenario, I'll see these large spikes in orange are as a result of the bit errors, because the bit error could occur on a most significant bit or a least significant bit. If it occurs on a most significant bit in the 8-bit pattern, then it creates a large amplitude error. I think I'm done for now. I need to wrap this up and get this into production so I can have it posted well before class today. So look forward to people joining through Slack, and then we'll do a video conferencing session where I can further share my screen and we can talk about the homework problems. So I'm going to sign off and say see you later.